Welcome to LIB Academy. In this video, we are going to look at the expectation value of the Hamiltonian square. From our previous videos, we know that the general time independent Schrodinger equation is h hat psi equal E psi. And the square, where h is the Hamiltonian operator, psi is the wave function, and E is the eigen energy value. And we prove that if we square the Hamiltonian operator, the energy value will also be squared. In this case, we are going to look at the expectation value of the Hamiltonian square. We also look at what expectation value means. The general definition of expectation value to be as integral from negative infinity to positive infinity, the complex conjugate of the wave function and the operator corresponding the observable, the wave function over all space. If the wave function is in terms of x, then this plane becomes dx. In terms of x and y, it becomes dx dy. We proved this in our previous video. You can feel free to check out the playlist. The Hamiltonian operator represents the total energy of a system. So expectation value of Hamiltonian operator simply means if you have a system and you are to measure, a quantum system, and you are to measure the total energy of the system, you continue with the experiment. You measure the energy of the system repeatedly, about let's say 3 times, 7 times, 10 times. The average of those measurements is what we call the expectation value. So you are measuring the probability of a quantum, of the energy of a quantum system. So the average of those probability is what we call the expectation value. And this, if it is an energy, expectation value of energy. So we have to look at the expectation value of the Hamiltonian square. So expectation value of the Hamiltonian square equal integral from negative infinity to positive infinity, the complex conjugate of the wave function and the operator of the Hamiltonian square, then psi dx. In this case, if the wave function is in terms of x. If you are performing the measurement on the x-axis, in 1D. So let's proceed. This equal integral from negative infinity to positive infinity, psi star h hat square psi. Let's put this term into bracket, the x. And from the general Schrodinger equation, h hat square psi is the same as e square psi. So we can replace this term by e square psi. H hat square psi equal e square psi. So we can replace this term here by e square psi. So psi star e square psi dx, integral from negative infinity to positive infinity. And now, because e is a constant, we can factor it out. E squared integral from negative infinity to positive infinity psi star psi dx. And psi star psi is the same as the probability density, the probability of us finding electron in entire space which is integrating from negative infinity to positive infinity, should be 1. The electron must be found within that region. That is if it exists. So this whole term here equal 1. And this whole term here can also be written as integral from negative infinity to positive infinity absolute psi squared dx e squared. And don't forget, this is the square of the expectation value of the Hamiltonian square. Sorry, this should be multiplying. So if this term equal 1, then the expectation value of the Hamiltonian square should be equal to the square of the allowed energy value. So far the identities that we prove is that if we find the expectation value of the Hamiltonian operator, it should be equal to the allowed energy value. That is for a stationary state. If we find the square of the expectation value of the square of the Hamiltonian operator, it should be equal to the square of the allowed energy value. So those are the identities that we need to know in quantum mechanics. That is it for this video. See you in my next video. You can feel free to check out my playlist on quantum mechanics. If you found this video helpful, kindly subscribe to my channel and give a thumbs up to this video for more educational content like this. You can also refer my channel to your friends. Thank you. Bye.